Let's do it.
All right. Good afternoon, everybody. I'm Devin Best. If you're here to vote, you're in the wrong building. If you're here for the Adelaida Hydro discussion, you're in the right department. I'm with the Upper Salinas Los Tablas Resource Conservation District. We've been working with USGS and the County of Public Works for a number of years on the Adelaida Hydro study. And what we've been doing, it was after kind of following the development of Sigma, there was an outcry of the community that came to the Board of Supervisors saying we need to do a study on this Adelaida hydro or Adelaida area. And the RCD partnering with the county and USGS said we can help work with to find some different landowners that would be interested in participating in this study. And having the county being sort of the warehouse of all this, but then having the scientific background to help support what we're doing going forward. And we're actually just coming to this is our fourth community meeting. Is that right?
Sorry.
Fourth or third, somewhere in there. And the first one was just, do we need to do a study? And that was kind of task one. And then now today, we're going to talk about what we call task two, which is a lot of the data collection that's been coming through in this last year that USGS has been doing and some of the roles that the RC has been helping to try and get relationships built with the local landowners and et cetera. So I'm going to actually introduce Jeff Cromwell from USGS. He's going to be doing most of the presentation. I think there's a slide or two for me to kind of present about a unique opportunity for folks that want to come out and actually see what all this studying does and how you actually go about and collect the data sample. And I'll talk about that whenever Jeff tells me.
2 minutes.
2 minutes. In 2 minutes. All right. So with that, I'm just going to turn it over to Jeff and then I'll be back up on stage. Right. Okay.
Thanks, Devin. My name is Jeff Cromwell. I'm a geologist with the U.S. Geological Survey with the California Water Science Center. Also here today from the survey is Joe Fackrell. He's a colleague of mine, and we're working together on this study. And as Devin said, well, first of all, we're recording the presentation, and so the audio is recorded as well. So this will be posted online on the county's project webpage and the RCD's project webpage as well. So just everyone's aware. This study is what I'm presenting today is work performed by the USGS in cooperation with the San Luis Obispo County Flood Control and Water Conservation District. And the Upper Salinas Los Tablas RCD is supporting this project with community outreach and setting up this meeting, for example, and has been a nice partner in the study going forward. So what I'm going to present today is the summary findings of task two as it currently stands. There's still a few more months of work that we're planned to do. And I'll be presenting work and data that are collected by the USGS and preliminary observations that we can see from those data. So everything that is here is either publicly available data or observations directly taken from that information. So the scope of this presentation is somewhat limited, but I hope it's informative and to bring some idea of what the work has been done and what a future pathway might be for this study. So for this outline, I'll jump to Devin in a minute for this Willow Creek Conservation event. I'll go through the project purpose and scope and what we're hoping to achieve in this particular project, a timeline of work completed so far and what we intend to do through this current round of funding that we have, a little bit of a description of the Adelaida area, and then we'll get into the hydrologic data that's been collected and some work that we're doing to develop a hydrogeologic framework model of the area. And then together, the hydrologic data and hydrogeologic framework, that information can be used to put forth a future interpretive product or something that's more holistic and comes together and say, hey, what does this actually mean? What we're just putting out here is results as they stand today. We'll go a little bit about next steps, then of course open up for questions as we have. I've got 35 or so minutes of information to present. I'll focus on the hydrologic data collection. If there's time at the end for the hydrogeologic framework, I'll present some of that. We can always talk more later too. So Devin, come on up.
Yeah, so the RCD actually was donated a piece of property off of Willow Creek Road on 750 Sleepy Farm Road as well. If you guys are familiar, it was the Justin property that was done in 2016, and they actually donated it to us so that we can actually develop a regenerative ag workspace. And so we've actually, that process has been going forward. The land was donated to us in August of 2023. My staff and I are working on some different programs we're going to be providing out there. But the reason we took on that is that we can create this regenerative ag workspace and provide opportunities for people who are interested in different things that are going on in the community, an opportunity to see them done here at our workspace without having to take on the risk and liabilities of whatever that may be. So an example of that is if you are interested in to see what well monitoring looks like, we can put on an event. And we actually have a couple sample points at our property that I think is going to be presented in today's presentation. So you can see what this whole Adelaida hydro study and what your role would be if you were interested in participating. And then also at the same time, if you wanted to actually go see what it takes for USGS to come out and do a data sample well meter reading, is that the best way of describing it? You can see what is involved. And so I'm actually looking to Eli, who's our conservation technician. He's raising his hands. He's the one that's going to be helping spearhead this event. It's on March 8th. So next, not this Friday, March 1st, but the following Friday, March 8th, where they're being cooperative. So if you're interested, sign up. I left my card in the back of the room, but you can also go to our website and find out about this as well. Or you can just find Eli and today and get signed up to go to that. We have, yeah, go ahead. You have a question?
How many acres were donated?
358 acres.
That was all clear cut, right?
Not all of it, but a good portion of it.
So are you planning?
Yeah, and I don't want to spend too much time talking about the property because I want to focus on USGS, but yeah, we are, part of our role is actually help do restoration, regenerative ag workspace, and then community meetings and stuff like that. So yeah, we are actually going to plan on replanting a good portion of it. But again, if you want to come out and take out a look at the property, more than welcome to come out on March 8th. If you want to see about USGS, that's also a great opportunity to see about all that as well.
And what time on March 8th?
What time?
Say 10 a.m.
We say 10 a.m. I think it's still being ironed out, but 10 a.m. It's a good time for everybody. Wake up, have some coffee, get a pastry, and head on out. Any questions about the event? Oh, okay, turn it back over to Jeff. Thank you.
Thanks, Devin. So I'll be there, and Greg Smith, and one of our field technicians, he'll be out there, and want to drop a tape down a well and see it beep, and that's a good opportunity to do that. So for this project, the county has a specific, came to the USGS in this cooperative study. They have a specific need to evaluate historical and current hydrogeologic conditions in the Adelaida area. And our purpose and scope here is to characterize the hydrology of the area. And to do that, we want to compile and collect geologic, hydrologic, and hydrologic information, quantify the hydrologic budget, and then refine the hydrogeologic system, the understanding of that system with respect to geographic, vertical, and temporal changes in hydrologic conditions. And so not all of this is being done right now, but this is in the scope of the project. This is the overall goal. So task one was data compilation, and this work was completed in spring of 2021. This goal was to compile all publicly available information that might be relevant to future studies. This was, scraping databases, talking to landowners, talking to the county, USGS repository, whatever it might be, to understand what exists, what knowledge do we currently have. And task two, which we're funded for, was funding for data collection for a period of 2 years. And then in this time, we've installed and are monitoring 2 stream gauges. We've established a groundwater network and are collecting groundwater levels for a period of 2 years. We also collected water chemistry samples last winter. And the second task is task AEM. This is the hydrogeologic framework, and we're using airborne electromagnetic survey data that was collected by the California Department of Water Resources in 2021 to use that, the airborne data collection to help inform the construction of a geologic framework model. If you understand the Earth, then you can better understand how water moves through the Earth. So that's the goal of this particular task here. And this is work that is funded directly from the USGS. This work here is part of our cooperation with the county, so a couple of funding pots. We have our USGS project website. Some of you have seen, so you may not be familiar with project summary, interactive map. We can go to and you can access selected data sources, land use maps, geology, and also our all the data we've collected. That's another portal to click on different data points as well and see what information has been collected, and also contact information for myself. So there's that. So as we get into what is the Adelaida area, many of you guys live there or you've been there. You're stakeholders who have a vested interest in understanding the hydrogeology of this particular area. The Adelaida area is a blue outline. To the east, it's bordered by the Paso Robles groundwater basin. To the north, roughly Lake Nacimiento. To the west, the boundary is the Santa Lucia Mountains and in this western edge of the watershed on which the Adelaida is largely derived, or as we've thought about it and constructed it for the purposes of this study. And then it goes down south to about Atascadero. This is an inland coastal highland area. There are rural, domestic, and agricultural water users primarily. And over time, there has been an increased percentage of irrigated agricultural land, not necessarily an increase in the total land, but what we can see from some data sets is the amount of irrigated percentage. Groundwater is the predominant source of water supply in the area, and this is not a designated groundwater basin. I think this is probably the key question of this study itself. The Paso Robles groundwater basin is defined by the California Department of Water Resources as a basin, and therefore, as you all probably know, there's been a lot of investigation and a lot of interest in the management of the groundwater in that basin. Because this is not one of those areas, relatively little was known about the hydrogeology prior to the study, at least from a publicly available context and like on a larger holistic level. So this is really what we're working with here and trying to understand the system. I'm going to flip back to this image here. If you keep an eye on this boundary. So the Paso Robles groundwater basin, this is a surface geologic map. And on the right-hand side to the east, the Paso Robles basin, the map geology is primarily superficial sediments and semi-consolidated sedimentary rocks, more unconsolidated materials. As we look to the left, to the west in the Adelaida area, it's primarily mapped as being comprised of consolidated sedimentary rocks. And so there's a different geology, it's a different a system in the groundwater and surface water may behave differently here than they do in the Paso Robles basin. It's a different type of system. The main player here, the most prominent geologic unit, is the Monterey Shale, mapped here in orange. And there are other older sedimentary rocks. The Vaqueros sandstone is here in brown, might be difficult to see. And most of these greens here are Cretaceous sandstones. And underlying all that on the far left is Franciscan melange, where you might get your serpentinites. The Clow mine is over here, and they're pulling some of those materials, likely from the Franciscan Formation as well. These pink lines are fold structures mapped by the state of California. We also have a series of faults that bound the area to the far west and then also to the east. We've removed the geology for now, but what I want to show here is this is a database that what is being projected on here are irrigated and usually irrigated agricultural lands. And the point isn't so much that these are ag lands, but it's the fact of where they are located. So in the Adelaida area, most agricultural land and also domestic users, folks who live out there, are generally located on the Monterey Shale. So the point of this is that you can see this overlay. This is where people are living, and if they have groundwater wells, they're likely spudded in this formation and may be withdrawing water from the Monterey Shale. People may also be drawing water from the surrounding and underlying rocks, which may include the Vaqueros sandstone and the other older Cretaceous sedimentary rocks mapped here in green. Also present in relatively small amounts is superficial sediment. The superficial materials are similar to what's in the Paso Robles basin, but you can see they're very few and scattered and located mostly along the stream channels. So a little bit about the shale. The Monterey Shale, it's late to early Miocene. It's a marine sedimentary rock, and it is very heterogeneous. So it is not a shale that you might think of that you're pulling big, I don't know, eels and fossils, like big whales out. And that's not, I shouldn't say, but it's that flat brown. It's not that. It's not plate. Something a little bit different. So there are different parts to the shale here. So this is a heterogeneous thing. And so as we think about where water may be withdrawn from, this geologic context is how we're thinking about the data that gets collected and how we want to move forward. So it's not just what's the water doing, but again, we need to understand the earth from which it moves through. So two different pictures. On the left is an example of some Cretaceous sandstone. This is by one of our stream gauges. On the right, you see an image of the Monterey Shale. If you've been out there, you recognize this pretty easily. Here you have this tilted bedding. You can see the planar bedding. In the Monterey Shale, there's presence of fractures. And here in this upper right image, you can see the synclinal fold structure of the shale itself. So this area, the materials are likely fractured, and they're also folded, and something that you can see throughout. So rather than maybe a more classic sandbox, there is some geologic structure in here that may or may not influence groundwater flow. We'll jump to task 2 in the data that we've collected as part of this study. We've collected 3 types of data: surface water flow measurements, groundwater level measurements, and also water chemistry information. And as part of this 2-year effort of work, we've established a monitoring network. And our goal is to record present day hydrologic conditions. You know, we're starting from a blank slate. And these data that we do collect can be used to evaluate the groundwater system. And all the data that USGS has collected is in our national, our NWIS database. Here's a link here. If you were to Google USGS NWIS, this would take you to this data repository. It is not user friendly. But contact me, I'll help you. It's here we are. This is our Adelaida area. You can see this little swath of colors that are up here. What each of these colors represent are different watersheds within the Adelaida system. You can see as we were trying to partition this area out for the study, we divide it on the east by the groundwater basin, and then these are all surface watershed boundaries that are here. The two main ones that will be of interest for the study is the Paso Robles Creek watershed. This is light tan color here, and then the Las Tablas Creek watershed. The Las Tablas Creek watershed flows from about the center of the study area north to Lake Nacimiento. Paso Robles Creek watershed flows generally south and then to the east and discharges at in the Salinas River. I'm not going to show. You'll see these colors again and again. I'm not going to show this explanation again, but I just want you to know these are the surface watersheds, mostly for reference, and they, at least for me, help me think about different parts of the study area that's there. So prior to 2021, the onset of the study, at least in the USGS record, there were only 3 groundwater wells. There were 9 surface water sites in the main part of the Adelaida area. And since the onset of the study, we've added information for 71 groundwater wells and added 2 additional surface water sites. So the amount of information has increased substantially. We don't have data collected necessarily from all of these, but we have well information from some of these. But so, this area of coverage has increased substantially. There are still data gaps. There are areas, especially in the north and east, which are primarily ranch land, and we either have not been able to get a hold of landowners, or there may not be anyone there. And over here, just where there's fewer populace, we are less successful in finding wells to measure and to monitor. So at least from what we have, this area of coverage is not inconsequential. Yes. Six.
Where's 101?
101 is here along the Salinas River. 46, here's 41.
Where's Adelaida Road?
Adelaida Road. It's coming out. It's Chimney Creek. Here's Adelaida Road. Here's the Cal Fire Station.
And you said you haven't collected data for some of these added wells? You said you added 71 groundwater wells, but you hadn't collected data from all of them.
No, we have regular groundwater level monitoring from about 60 of them, or from 60 of the wells. Other wells either were, we recorded the locations, landowners have been interested in participating, but we may not have been able to actually physically take a measurement. Some wells, we have to a little bit have provided well intel information, but we're not able to take a measurement for that site. So this is the collection of wells that people are willing to let us at least try to sample and get some.
I've been
Yeah.
reporting to the State Water Board since 2010, monthly usage, and they have all the records. The State Water Board, they were going to fine us
Okay.
unless we reported.
Okay.
So we complied, and so we have so many records. They have so many records of so many wells,
Yes. Thank you. Okay.
and I do too,
Okay.
because I've started doing it.
That'd be great to share. We have access to the Department of Water Resources, and we have, we're aware of the State Water Board and some of the reported pumpage that's there
Yeah,
too.
annually, they check now.
In the Adelaida area as well, or in addition to. Okay.
Yes, everywhere around, because we were in a riparian,
Got it.
and they said we were in the Atascadero Basin,
Okay. Okay.
but you said it's not in a basin?
2 different things. There could be, sometimes surface watersheds are referred to as surface basins for surface water flow.
Yes.
So this is not a groundwater basin. So it'd be a different sort of
Oh, yeah, yeah.
designated groundwater basins. and there might be surface water
There's
basins,
both.
sometimes referred to as basins as well.
Yeah, it can. It's both.
Yeah, two different things, but they could be on top of each other. Or
Well, yeah, that's where it comes from.
gotcha. Okay. All right. Great. I'll look for that and talk afterwards would be wonderful. Okay. Yeah.
Do you have a list, since you started your study, of the wells that have been replaced and the locations of those wells with the new information from environmental health on how those wells were constructed, if they have been replaced, and what depths they were at originally and what depths they're at now?
We haven't looked specifically at replacement wells. Our database that we compiled at the beginning of the study is from 2021. Moving forward, we will do a new scraping and collect a new set of that well construction information just to see what else is new in there. But our goal isn't identifying specific replacement wells or not, but we will collect new information that comes in.
Well, just to show you, because I have from 2014 to the present, all the wells have been replaced over the Paso Basin. And that information is readily on hand from environmental health that gives the permits for those wells. And I just recently, somebody sent me the ones that have been replaced here. I haven't been able to download the information yet, but it gives you the well construction and everything along its permit, so you'll know what the old well used to be and what replaced it.
I see.
And those people, I'm on the technical advisory committee for the Paso Basin Plain Reel. I've been involved for 11 years on that stuff. I'm in the watershed in the Crescent area.
Mhm.
And I'm the slow cattlemen's representative on the Water Resources Advisory Board. And for 8 years, I was Debbie Arnold's person on the water board.
Okay.
But that information will specifically, those are the people to contact if they replace their well. They're willing to do that to see that they have new information. We're trying to provide equipment that we already got funding for 130 new test sites, and they're trying to develop some kind of outreach with a document that the people will share the information.
Okay. All right. I'll note that. Thank you. And yeah, perfect. Thank you.
Greg Gribble.
And then
Okay.
I was just gonna jump in. Part of your comment was, we actually, in a previous community meeting, we actually showed all the different wells that were out in Adelaida Hydro. So that was how we first said, well, there's a lot of wells. We'll only have a couple data points. So that's where, like Darcy, we started kind of helping with USGS, kind of trying to identify, well, where we have gaps. And can we start working with folks to actually get them to actually be a data point that they can use, not just, yes, we know there's a well, but we don't know if anybody's using it, if it's useful. So I think when we showed like all the wells that were in the area, it was like this huge grid of wells all over the place.
Over 1,000
And this is where we did a big outreach effort saying, out of all the people in the community, how many of you are willing to provide data so we can start developing a study? And this is where we've gotten to today.
And we did targeting contact as well based on where well information was, but I appreciate that for moving forward. We can
Yeah,
identify
because
those.
what we did at first was to identify where the shallow well problems were.
Mhm.
They were 4 main areas.
Okay.
And in those main areas, then we could identify, those homes were allowed to have shallow wells before the irrigated ag came in around them. And then your irrigated ag in this area was the increased irrigated ag was a automatic reflection of the emergency ordinance that was passed in the Paso Basin on not being able to plant where people moved to the west so they could plant. And so
Put that as well.
it's good to identify the specific areas where new irrigated ag went in and what happened to the wells in those areas.
That's a huge question. All right. Thanks.
He knows so much about water. Oh my
Yeah.
God. He is like a computer. And it's accurate.
So you got me here.
All right. So we'll talk about the 3 data collection. We'll do that in order. So with surface water flow, groundwater levels, and then we'll get to water quality information. So we've installed or reactivated 2 stream gauges, a new gauge along Paso Robles Creek. This is the USGS site number. We reactivated a historical stream gauge along Santa Rita Creek, and we are continuously monitoring each of these for a period of 2 years. And so we will monitor these through our current funding for the end of December 2024. So it's for the end of this calendar year. Here are the 2 stream gauges. This one, here's this box, this inset, here's the enlargement. This is the Paso Robles Creek gauge. I'm here at the downstream end of Paso Robles Creek, right near where it exits into the Paso Robles Creek, or the Pascadero subbasin. It is. This is the Paso Robles Creek watershed. Here's the Santa Rita Creek watershed coming in. This is the historical Santa Rita Creek gauge and at its location, which then feeds into Paso Robles Creek, and drains out.
Same place where it got blown out last year.
Which one? The Paso Robles Creek?
Yeah.
Yes, but higher. So this is the Paso Robles, couple images. This is the dry creek bed during installation. This is the electrical box where all the goods are, the sat link, the solar panel. Then you have the feeder line down to the orifice here. Here's a staff plate for measurement and comparison purposes. Here's a picture of the creek with flow. And this is from our field crew, James Solomon, and the Santa Maria field office is managing both of the stream gauges and doing the measurements and QA QCing the data. This line across here in this kayak is what permits our field techs to go out and take physical discrete measurements. And so the physical measurements that are collected are used to basically calibrate the sensors that are pulling water continuously, pulling information continuously, and the physical measurements allow for a rating, so you can determine what this tells you is how high the water is. What these calibrations then tell you is allowed to convert that into total stream flow and discharge. And so it's two different things, and it also allows just to make sure that the instrumentation is working properly by having physical monitoring out there. So same images on the right. This is a hydrograph of all data that has been collected at this site beginning in October of 2022, where there was initially no flow. See there, going through January 22 of this year, so just the last month. On the left-hand side is the gauge height in feet, so that's how high the water level is in surface water. Calendar year, this is time. This is all the different flow periods, or how much it's flowing, stage height, and overlaying this with on top is precipitation collected from the Western Weather Group gauge and then your drive. There's no scale bar here, but the max precipitation was 6.3 inches, and this is 0. You can see the responses in most cases to a precipitation to flow. And this is your question. This was at the high point in December. This was January 11, I want to say.
January 9th.
January 9th. And so this was our gauge, and we since moved it. But thank you to the folks that let us have that there. This is the Santa Rita Creek gauge. This is an old stilling well that was put in at some point in probably in the 60s. This has a housing. This is it as it's been refurbished. We see the orifice line heading out into the creek. There was flowing water, or there was water in the creek when it was installed. This is the view looking upstream. Over here, this is looking to the left. Downstream is to the right. Same three images. And this is also same hydrograph, same time period from October 1 to January 22nd. You can see the hydrograph here. The gauge height is substantially lower. See, this goes only to about 8 feet, and the previous one at Paso went to above 25. Excuse me. We can put on the precipitation. So we didn't get it installed in time for the January events, but we were in for the March events. This is the entire record of the Santa Rita Creek gauge. So it's historical information from early 1960s through 1994. And so there's this historical record. This is daily discharge shown here. This is our current study. So we have just under a year's worth of data so far. And the value of reactivating this gauge is to be able to compare what the present day conditions are to the historical record. And at the moment, we can't really do that because we have 1 year's worth of data and one exceptionally high storm event, at least based on recent history. So more monitoring, more information at this gauge in particular in the future will provide for some record and some context to how things have changed or not since the middle part of the century. That's a good question. The funding stopped and people paying for it said no. We have a hard time tracking down. This was our office, but we don't really know the reason why. No one was around since then. I think this was largely a sediment transport study. There's a lot of, sediment load information in the Santa Rita coming from this gauge. But that study, whatever it was, stopped. But at least we're grateful that this information is still here. So groundwater level monitoring. Our same map. This pinkish color here, each of these dots are one of 60 wells that we're doing regular groundwater level monitoring from. 60 wells, 26 are domestic use, 8 are irrigation, 18 are mixed use. Probably mix of ag or mix of irrigation, mix of domestic. A residential house on a vineyard, might be some of that. So it depends on the size, what property is there. Then 8 unused wells, and these are generally wells that there's the plastic open casing. There's no pump in them. So those actually are very valuable from a monitoring perspective. At each of these sites, each of these wells, we're collecting quarterly measurements every 3 months approximately. First started for this project in August of 2022, and we'll run through June of 2024. So June of 20, we got 2 more measurements. I've contacted everybody today. So next week we'll be out again. And then the final measurement we'll have will be in June of 2024. There are 2 sites that we are doing continuous groundwater monitoring. So we have a pressure transducer and 2 wells. And these are both at the RCD Sleepy Farms property, collecting hourly measurements. So I'll show those curves in a little bit. We also have data furnished from landowners. So these are landowners who have well intel systems or drop control and have been downloading their data and sharing it with us. So this is something that we have in our hand, which is useful because many of these sites have longer term records than our 2 years of data collection. So it's valuable to have some at least qualitative relative sense of groundwater level before, prior to the start of the study. I'm not going to show any of this information, but we have it. Again, we're focusing on the USGS data that has been collected. And all the groundwater level data are in the USGS NWIS database. Each of these wells, from which we have every well the USGS has in its database has its own landing page on our NWIS data site. And all landowners who we collect information from, we've sent you the links to access your well site. If you don't have it or you want another one, I can send it to you again. Just let me know. Here you can click on the field groundwater level measurements. This particular well has water quality samples. You have the beginning date, the end date, and also the well information, latitude, longitude, well depth, hole depth, and then the surface elevation of each of those wells. Same map, shifted to the left, different dot sizes here. So now I'm going to show is the data that we've collected. And what I'm going to focus on is the groundwater response to last year's winter storms. And so this is going to show changing hydrographs and changes in elevation, again, focusing on just last winter. So we had a very dry period before that, several years, this big winter storm. What happens to the groundwater levels across different parts of the area? And what these dots are representing is the increase in water level elevation from our December measurements to our May measurements. So in between that really was that period of wet storms, mostly in January, mostly in March. We took measurements in February, kind of in the middle of it. So let's take from the very beginning of December to the very end of May. All wells that we measured saw an increase in groundwater levels ranging from about a foot to about 126 feet. So these smallest dots are the smallest increases in groundwater levels, and the biggest dots are those with the largest increases in groundwater levels. This is an example hydrograph from this well here near the edge of Lake Nacimiento. And each of the hydrographs I'm going to put up is going to have the same set of information. This curve is going to change based on the actual water levels measured. But this first measurement here is going to be August of 2022. This will be December of 2023. This is the approximate extent of the 22-23 winter storms. And the scale on the left-hand side is the same. So each of these tick marks is 25 feet. So these are all going to be scale stable. So you can see the relative changes of these relative to each other. So this particular well from December to May went up about 25 feet in this location. So same well, I shifted it up there, and the rest of the ones that are going to pop up are going to be this size, the same set of info. This well here from December to May went up about 100 feet. This well down over here on the far eastern part of the study, maybe another 20, 25 feet. This, I think, was the biggest gain. This looks to be about 125 feet, and this was the biggest increase we saw. This well saw almost no water level change. 5 feet. Sorry, that's down here. And these two wells cluster together. This upper one in black went up about 25 feet. And this well, about a quarter of a mile away, was up about 100 feet over the same period. And so the takeaway is that the response is variable. The response depends on the location within the study area. It may also depend locally on location of streams or not streams farther away. It may depend on geologic unit. It may also depend on well depth. And at least in the case of these two wells, this well is about 200 feet deep. This well is about 500 feet deep. And so in that proximity to each other, there's some likely condition of well depth and possibly geologic formation that is resulting in different groundwater responses to recharge events. Yeah.
The first time?
Yeah.
So how did it jump out without any precipitation?
There's the other variable in here is pumping and irrigation. And so there's two things that happen, right? Following the summer period, irrigation is generally declining, and then you also have rains coming in. So that's another factor to consider of why are groundwater levels changing the way they are? Geology, previous pumping, proximity to wells, recharge, that's all part of this equation of questions for us to think about. I'm jumping here. I'll go back to this. Oops, big cursor. This is the RCD property. It's this cluster of wells. Nope, this cluster of wells right here. We are inset. These are the two wells. We have USGS pressure transducers, PuO2, PuO5. PuO5 important feature is it's only a few hundred feet from Sheep Camp Creek. Sheep Camp Creek is an intermittent stream. In the summer, it doesn't flow, but it most certainly had some flow in the winter. This well is also spudded or is drilled in what's mapped as superficial sediment, so more unconsolidated materials. PuO2 is about a quarter mile to the north and to the west here. This well, about a quarter mile from the creek, and it is spudded or drilled into the Monterey Shale. There are two pumping wells nearby. One was installed soon after we started our monitoring. There's another new well that was installed a little bit to the south, just off the edge of this picture. These other smaller dots are other wells at the property that we have groundwater measurements from. These are both unused wells. They're both open casing wells. There are no pumps in them. So here's the plastic casing with a mushroom cap on top. Here's a little bit closer image. So the pressure transducer will sit and basically drop down, and it's held. And there's a little, hopefully rodent-free box of electrical cables that hold it. You can drop a rock down there, no splash. And so these are open to us. These are very valuable from a monitoring perspective. And these are the curves for the hydrographs for each of these wells over the period of record that we have the transducer data. Most of the transducers were installed just about the beginning of March of last year. We look at PuO5 first. Over the winter storms, they had a more rapid increase, more rapid response from the precipitation events, and a steady decline until about here when you start to see these wiggles, and these are going to be likely a pumping response from nearby pumping. PuO2, a little bit further away, has a much more gradual response to the recharge event, and yet it stayed relatively stable. And you don't see, if there is any response to the pumping signature, it's very, very minimal on the scale. And sorry, this is plotted as groundwater elevations. This is not depth to water. This is the elevation of the groundwater system. So there are two new wells that we knew in part of looking at these hydrographs. Okay, what's happened? What's different? But we believe we identified when these two new wells were constructed, and this is likely the onset of pumping, more regular pumping. You can see that intervals. So again, different geology, potential different response to recharge, might be infiltrating more rapidly along the stream system than further in the Monterey Shale. You have distance from the pump. Why aren't they talking to each other? Well, there could be, we saw those pictures of the tilted formations. There could be a geologic influence that's preventing that connection. So a lot of unknowns here, but we see in the data that there's something interesting. Yeah. Uh-huh. It's likely due to pumping from those wells that are, but there's a new well that's installed there and they are pumping from it. And these are very, very close to each other. So yes, it's probably a pumping signal response. So it's not, the point of this is not that somebody's pumping. The point is that there's a pumping response right next to each other and not in this other well. So this is we're coming back to this diagram. And what I'm going to put up here is a conceptual diagram of a groundwater flow system that may or may not be representative of the Adelaida area, but it's something I think that can provide a visual. So this is going to be A is going to be here in the Santa Lucia Mountains, and then to the right-hand side, A prime, a conceptual diagram of the flow system. And I'm going to put this up here, and then we'll show it again when we get to the water quality. So a couple different parts. So here's A, this is on the left-hand side. Maybe it's something that's over here where you have the higher elevation in the mountains, and as you would go down in topography in general, as you get to the Salinas Basin, Paso Robles Basin. I want to draw your attention to these little arrows here. So in a conceptual groundwater system, you might have local groundwater flow, which is recharged by local areas of recharge, and there may or may not be interaction with surface water for little streams that are there. You might have, and so these would be relatively short flow times, short flow paths from recharge areas to discharge areas at streams or further down. You might also have more sub-regional flow systems, something where the amount of time in the groundwater system, these flow lines have been moving for longer. The water is probably older. It's been recharged more in the past, and it's likely going to have slightly longer flow paths. You might also have a regional flow system, where this is from the main point, a regional point of recharge. This groundwater would likely be the deepest, likely take the longest time to flow and discharge, and it's also likely to be the oldest. So in this conceptualization, we're seeing in all those variabilities. And one thing that we don't know yet is whether we are looking at a local flow system, what we're measuring and comparing to, or perhaps a sub-regional flow system or something longer or bigger. So in this conceptualization, points to some of the uncertainty that I think I've demonstrated, that there are changes, there's complexity here that isn't readily answerable. So now that we've talked conceptually, we look at we have groundwater level elevations. We know groundwater moves from higher groundwater elevation. It moves downhill, high to low. So we can take the water level elevations that we have, and we can essentially connect the dots to what's the likely flow direction, at least based on the measured points that we have. So in the back, I did test this. This is small. I'm sorry. So these are estimated groundwater flow directions. The size and the length of these arrows is not proportional to whether it's a local system or a sub-regional system or the magnitude of groundwater flow. What these are essentially doing is connecting the dots between areas of higher elevation, groundwater elevation, to areas of lower groundwater elevation. So what we can at least observe from this first order analysis is that the flow from higher groundwater altitudes may go to the northeast, to the southeast and to the northeast from the Santa Lucia Mountains, from these higher elevations. We start to see, there's a direction of flow here. We might also see from higher altitudes in the middle of the study area where the Monterey Shale is exposed. I might see flow to the southeast towards the Salinas River down towards the Paso Robles Creek watershed, and in the opposite direction towards Lake Nacimiento from the northwest. So in this pocket of area, the flow may or may not be controlled by geologic structures. It may or may not align with surface drainages, maybe on a local scale, perhaps on a big scale. Those are all questions that we want to answer. But this can be evaluated. These questions can be answered by using the geologic framework, understanding the geologic structure. Using that airborne EM data in particular can help identify variations that may not be something that be captured from well data or map data. And also the water quality data will play a big role in understanding the groundwater flow system. So we'll jump now to water chemistry. This is the last set of data that we collected as part of task 2. We collected 14, there's samples from 14 wells and 3 surface water sites, so both of our stream gauges, and also another surface water site at West Topless Creek. This was collected in late February, early March of last year. We sampled for a range of major minor ions, and then various isotopes that can tell things about the groundwater flow path, and especially isotopes of tritium and carbon that can give a sense of groundwater age and may help answer that local versus subregional versus deeper flow path of water. So the water chemistry data is very useful in characterizing the sources of movement of age of the groundwater. You can also identify the source and climatic conditions at the time of groundwater recharge. So it can say, a couple different things about where the water has been and where did it start from. And I'm putting this geology on again, just for comparison, you can see where our wells are located. We selected our wells to get as we could identify, we try to capture wells that were likely withdrawing water from other units besides the Monterey Shale. We're limited to what we have available to us. But we captured a few outside the Monterey Shale. We captured a few that we think are actually drawing water from something else and deeper. And this is our, this is our schematic. What this can help inform now is, okay, are those sort of initial flow directions something that are reasonable, or should we be thinking elsewise? I'm going to put 2 diagrams up, and both of these are related with respect to US EPA contaminant levels for drinking water. One of the contaminant levels is the maximum contaminant level. This is something that, at least for public supply water, groundwater or water cannot exceed those levels. There's the secondary maximum contaminant levels, which is something that is recommended that they don't go over. So for a water quality or water taste and color and perspective. So most major iron concentrations are below the EPA MCL or SMCL for across all the wells that we measured. There's a few here and there that might go up, but in general, the major ion concentrations fall well below these values. And the ion concentrations in groundwater may be and are likely associated with the geologic units through which that groundwater flows. And all these water quality data are in NWIS. So up here, I'm showing total dissolved solids. This is not any one constituent, but this is a combination of the additive amount of solids that may be in the water. This is the EPA MCL, 500 milligrams per liter. You can see most wells exceed the secondary MCL, this recommended amount for total dissolved solids. If you don't, these are the surface water sites here and here. These are, and then here's the milligrams per liter concentration for this total dissolved solids. These are just by sample date. There's no order to how these samples are presented on this graph. They're just another one that may be of interest, and to show some of the variability here. This is nitrate in water samples. The EPA MCL is 10 milligrams per liter, but you can see nothing exceeds 0.5 milligrams per liter. So this is a constituent which is very low in the Adelaida area. In areas where there may be a lot of agriculture, one might expect to see higher nitrate concentrations. That is something that is not observed in these samples that we collected. The last water chemistry bit I'll show today is related to age dating. And we're showing 2 different constituents, parameters on this graph. One is carbon-14. This is the percentage of modern carbon. 100% would be something that is entirely, it rained yesterday, would have 100% modern carbon. And that is something that we would see like in this surface water sample. This is from a tritium sample from coastal California precipitation, essentially yesterday's rain that's in groundwater. On the left-hand side, on the y-axis is tritium. And the more tritium, well, tritium is an on or off switch. So tritium indicates the presence of detectable tritium indicates recharge after 1952. So tritium is naturally occurring in the earth, but usually at background levels. With the onset of atomic testing, the 1950s, now they put a whole bunch of tritium in the air, and the rain hits the tritium, brings it down in the groundwater. And so if you find detectable tritium in your groundwater, it has been recharged, or some fraction of that water has been recharged since 1952. So modern, recent recharge versus something older than that. And we can also use carbon-14 to get an estimate of the actual age of the water. So you can go back, 1,000, 10,000 years or so to get an estimate for that actual age constituent. We're not showing that here, but we're just showing the relative amount of percent of modern carbon versus basically in the tritium concentration. Three the wells, this is only groundwater we're showing. 3 wells had no detectable tritium, meaning that they were recharged entirely before 1952. All other wells had some fraction of the water that contained tritium. So the tritium is detectable. It doesn't mean that all the water in that well, then gets pumped out and put in this bottle. It wasn't all recharged since 1952. It just means some of the water, some fraction of that got pulled out in that sample is modern recharge.
Is there any wells that are not been recharged by since 1952, like? On the east side?
That's a good question. I have not looked at that. There probably are some. That's a very good question to compare to. I'll look into that. And correct me if I'm wrong, Joe, it's not uncommon to have water that's tritium dead. That's pretty typical. So it's not uncommon to see tritium dead water in deeper groundwater wells. So that more, if you're pulling water from deeper down, that's picking that more regional flow path, that's more likely to be tritium dead. So this map view is showing our same purple squares and red squares. These are the locations of the 3 samples that are tritium dead. These are the locations of the other 11 that have some fraction of tritium in them, with our geologic map on there. And I'll throw this conceptual diagram here. Again, we're gonna bring this up again here. This is where we still have our local flow paths, our subregional flow paths, and our regional flow system. And so your shorter flow paths are more likely to have some fraction of modern recharge water, whereas your deeper flow paths, your more regional flow system is more likely to be tritium dead. So depending on, that's something you want to look at too. It's not very reasonable from this conceptual schematic. These samples may be at the end of a long regional flow path. So that's part of what the complexity here is that we're trying to understand. So the summary of current work. We've installed and are monitoring 2 stream gauges. We've established a groundwater monitoring network, and we have 2 more sampling periods next week and then also in June. And we have our collection of water chemistry samples. Groundwater level response to last year's winter storms was variable. Most wells have some fraction of modern recharge water. And lastly, there is likely a geologic influence on recharge response and water chemistry. And what is that? That's a question. We're at 52 minutes. This last bit is the task AEM. I'll move quickly through this, but what we've taken is this airborne set of data that can come out of this from this instrumentation. We're looking at electrical signal responses from the earth materials from this information. And this gives us the swath of colors here, where the reds usually are more resistive rocks, your more resistive electrical signals, your blues, as they're modeled, are usually more conductive materials. More conductive materials are usually clays and silts or finer grain material, or it could be more saline water. Then your reds are your more permeable materials, generally your gravels and your sands, something where the grains are just a little bit farther apart, a little bit bigger. The California Department of Water Resources, with our input, flew a series of lines in 2021 across the Adelaida area. These are the flow line directions. We arranged these such that they were generally going across the geologic structures. So we want to be able to see if faults and folds are behaving and what they're doing. This is part of a larger effort by the state to map most of the groundwater basins in the state with airborne EM, and basically build these framework models and look at the earth. We're very fortunate to coordinate with them to get something in this area. Same view. Here's our blue outline. Here's our geologic map. Here's the Monterey Shale in orange, Paso Robles groundwater basin, Salinas River. But we're tilted down a little bit. There's an 8 times vertical exaggeration. Here are the flight lines. And I'll throw the resistivity model that's on here from those flight lines. You can see the different colors. I'm going to rotate this to this orientation. We're kind of shifting around to the right. We're looking a little bit north and west. Here's our Monterey Shale in orange. These are the different flight lines, different resistivity colors. in the Paso Robles basin, at least from this resistivity model, there are more blues, more conductive materials in this location. As we move across to the left, the west, when we get into the Cretaceous sandstones, we start to see more reds and greens. These are the more resistive materials. As we keep moving west over the Monterey Shale, we start to see the presence of more conductive materials, more blues and purples. As we keep going back to the west, we get back into the Cretaceous sands and the Franciscan Formation, we see more resistive materials. And so at least from this, what we'll present here is that there does seem to be a response based on geologic formation. And so if we can look into subsurface, taking borehole data and lithology information, well construction information, we can start to pick out and maybe say something that, hey, this might be the bottom of the Monterey Shale that we're looking at here. So we can take this 3D perspective, connect the dots from the airborne EM, connect the dots with lithology data from the boreholes. We can start to make this 3D map of what the Earth probably looks like. And then we can, in essence, run groundwater through it, either conceptually or in a model in the future, and help understand that system. So for this work, we've reprocessed this information that came from the state. We've compiled borehole lithology and geophysical data, and we're working on a preliminary, we have a conceptual framework in mind, and we're in the process of drawing those lines and putting this together. So the next step, this is our work. Task 2 and Task 8 EM will be done by the end of this calendar year. And that's when the current set of funding expires and runs out. But so for the rest of the year, we're going to continue monitoring both stream gauges through December. We're going to collect groundwater level measurements through June. And the reason for this offset is that the stream gauges got installed later. We wanted everything to start in August of 2022. Stream gauges got pushed back 3 or 4 months. So we're keeping our 2-year deadline for the groundwater level measurements. And then we're just extending the stream gauges out just a couple months. So we still have that pocket of money dedicated to it. But we wanted to get 2 years of measurements. And then the framework model, we're looking to have an interpretive report in the fall of 2024, showing the sort of mapped 3D structure that we have. And because funding is well, running out, and we're getting to the end of the proposed work and the agreed upon work, USGS will present future work tasks and budget and scope to county staff this spring. And future work tasks may include continued surface water and/or groundwater monitoring, maybe at selected wells, all wells, new wells, some combination, which is where we think can enhance the interpretive ability of the study. Perhaps additional water chemistry sampling, perhaps focused hydrogeologic evaluation in different areas, and then also it may include, a USGS interpretive report. So right now, all these data are available, everything USGS collects. And if we were to walk away and shake hands and say thank you, at least this data is out there for someone else or some other entity that can, utilize this information. So if this were goodbye, at least I think there's been a very valuable contribution to this area and to the study. But I hope we get to continue and see you guys again in a year. So yes, thank you.